Welcome back, everybody. So to begin the afternoon, we're very pleased to have Ausoni speaking on the topological Hochschild homology of Johnson-Wilson spectra.
Thank you. Thank you very much for the invitation to speak here. It's a pleasure to be back. So I want to speak about joint work with Birgit Richter, who's here on the. Okay, so what it's about? It's Johnson-Wilson spectra. We're unfortunately not introduced this morning, but let me start with maybe topological Hochschild homology. Is the version of Hochschild homology for ring spectra. So we assume we have an S algebra and then we define THH as the derived smash product of A with itself as an A bimodule which is given by this. And if we were starting with an HZ algebra, then we would have ordinary Hochschild homology. Okay. Well, here we need to put HZ. Okay, what's the main interest of this theory, or at least a main interest is that you have a circle action on Hochschild homology that allows you to define cyclic homology, and that's somehow the input for the theory of cyclic homology, which is a great rational invariant of algebraic K-theory of ring spectra. And this S1 action that you have on Hochschild homology gets promoted to something much richer, which is a cyclotomic structure on topological Hochschild homology, something that you don't have if you remain if you remain in algebra, and that leads to topological cyclic homology, which in turn is a great invariant for algebraic K-theory. But in this talk, I don't want to go at this side of the story, which is also related to chromatic shift by algebraic K-theory, but to keep our eyes on THH. So why would we like to do that? Well, THH has some interest on its own. First, for example, you can use it to prove that topological K-theory is not a Thom spectrum, as Tyler did with co-authors. You can study what log rings are, if you have the right definition of log rings, for example, and so on. And since this is we can chromatic homotopy, we have been interested with Birgit about somehow a kind of blue shift that you have in THH. That is that you have lower chromatic pieces that appear. So if you study THH for itself, one of the fascinating things that you have to deal with are extensions, and I think that's really something difficult in THH is additive or multiplicative extensions. What do I mean by that? If the first example is Bergstedt's theorem that THH of Fp this is a polynomial algebra. While if you look at Hochschild homology, it's going to be a divided power algebra. I call this mu 0. And so this is somehow has a lot of torsion. In the class mu, the piece power is trivial, and then you have a new generator whose piece power is trivial, and so on. while here you have something polynomial, and that's of course very important for K-theory computations, but it's also in some sense quite mysterious. So here you have extensions from the algebraic case to the topological case. And I want to look at another phenomenon on multiplicative and additive structures today. It's an intriguing result for me. It's McClure-Staffeldt. So in 2002 there was a Newton Institute program where I shared an apartment with McClure and bugged him to learn everything about HHH. And unfortunately I haven't met him since, but it was a great time for me. What did they compute? They look at L. So this has been introduced by Agnes this morning, L, the Adam summand. Of localized K-theory, which splits as certain copies. And then they compute HHH, and they show that as an S module you have such a formula. Okay, and actually you can extend this to KU also. If you take topological K-theory, you have the same formula. And it's quite surprising that you have this rational factor that appears, and which you can think of somehow a blue copy of this when you think of redshift. And well, I was always intrigued and tried some effort to try to understand where does it come from, how can we account for it. And again, Tyler Lawson with his co-authors Engelbart and Hill gave an answer. So the rational part, well, they look at the connective version. So at this time I'll give the coefficients, which is just a polynomial ring on V1, the same V1 that was in Agnes' talk. And we have a formula, a localization. If we look at just the torsion, the V1 torsion free part, and invert V1, we are going to get HHH of L. So if you want to understand this picture, you are to understand the torsion, the V1 torsion free part in here. And what they show is that, okay, you have a, coming from the S1 action, you have a map from the suspension of L. This is coming from the, let's see the connected version. It's essentially coming from the S1 action. And the V1 torsion free part is given by the following picture. Well, you have in THH you have the unit, and then this multiplies by V1 to a polynomial part, and then you have this class sigma V1 coming from here, which is in degree 2p minus 1. And when you take this class and multiply by v1, well, it keeps going forever. But depending on the prime, at some point you have division by p. Okay. So when you invert v1 here, you get just some polynomial. And here it's a little bit like when in the divided power, if in a divided power over z you invert the element, you get something rational, right? So here you get by inverting v1, you had something rational. On this class, okay? So that's somehow an account from where this rational piece comes from, but it's somehow very, very computational also. And if you are looking for another phenomenon which is systematic, general, and not just for small n's, or here first Johnson-Wilson spectrum, it's something closely related, I think, is the Ravenel-Wilson computation of the Morava K-series of Allenberg-MacLane spectra. Okay. So they computed quite generally the Morava K-theory of Allenberg-MacLane spectra. Well, let's just take Z here, and they show that if M is greater or equal to n plus 2, then for Morava K-theory, the Allenberg-MacLane spaces are just like points. They won't see the difference of an Allenberg-MacLane or high-dimensional Allenberg-MacLane space on a point. Okay. Well, here it's very systematic. There are no other condition on M and N than this one. Probably you need N bigger or equal to 0, bigger or equal to 1. But it's very general, and this relates to this question here by the work of Bruno Stanek. So he studied quite generally what the tensor in the category of KU commutative algebra, what the tensor with finite spaces is, and he got the formula for THH of KU. This time as commutative KU algebras. Well, this is the group ring, if you want, KU based. Group ring of the group. Okay, so this is following quite easily from Snell's formula. That Nico talked about this morning. That you have a model for KU as commutative KU, commutative S algebras, you have such a formula, right? So this is a KZ2. And when you apply THH to this formula, you will get this formula up here. And by Ravenel-Wilson, we know that by Ravenel-Wilson, we know then that in here you have a copy of Ku, a wedge, a copy of the smash of Ku with KZ3, and this is rational. Okay. So in this formula, you have another explanation how this rational term appears in THH. That is somehow a bit more. I don't know how conceptual Ravenel-Wilson is. If we, I mean, it's a hard computation. I don't know if you have a conceptual reason why Morava K-theory sees high connected Allen-Bernoulli spaces as points, but if this is the case, then you have a more conceptual explanation here, right? And with Birgit, we asked the question somehow: will this kind of splitting with blue pieces will this generalize if we go to higher examples, higher chromatic example of ring spectra? So here L was just E1 when we speak of Johnson-Wilson spectra. And you have a whole family of them. Well, P for us will be an odd prime. So the coefficients of the Johnson-Wilson spectrum are the V1 to the Vn's, but the last one is inverted. Okay? So these are the Johnson-Wilson spectra that can be constructed with a complex orientation, given as a map from BP to N as ring spectra. So the question that we ask is, can we understand THH of these, and will we see somehow a similar splitting? Okay, so the strategy that we chose to follow is the one of McClure-Staffeldt. So first you compute all the Morava K theories. Okay. And then you use chromatic factor square to assemble the pieces. And that's how McClure-Staffeldt did it for the Adam summand. So maybe a remark here. Something similar was attempted by Bob Brunner and John Hognes. But otherwise, to take something that is commutative, so I think in unpublished work, they computed the Morava K-theory. Of TMF, and they get quite algebraically the answer is quite the same for these groups, for the Morava K-theory groups. So are there questions so far? So the first step, computing the Morava K-theories, is the fun part somehow. And the first proposition that we had, that is in some sense maybe implicit in McClure-Staffeldt. They did it for the n equal 1. I didn't state it further, but it's quite close to what they do, is that the inclusion of zero simplices, or the unit map if you want, this is a Kn isomorphism. Okay. So this is somehow a first indication that, okay, Kn will see just En, and the rest, the stuff, at least if you have some multiplicative structure, so that this is a module, it's going to be En local, and then you have that the rest has to be lower chromatic, of lower chromatic type, the cofile of this map, right? So that's already telling you, okay, you just from the eyes of Morava K-theory at level n, you just have the zero simplices somehow. And the proof is essentially also a computation, I think, that is due to Ravenel. I'm not completely sure about that. So we have to understand somehow the ring that disappeared. Okay. Well, we start with BP that Agnes, I think, gave us this morning, and we are going to compute this guy. And this is something that you find in, at least in Ravenel's book on complex cobordism. Like this, where the BP cooperation, this is also computed with the help of the formal group law, and then you have the left and the right units. Where we just say that they send the class VI to VI, and the right unit will be mapped to class that we call WI, okay? If you can read around there. And then the formula that you find in Ravenel's book is that well, that's just going to be this first part, and then you have to mod out by these, and here you have formulas for these that are of the form and probably is this correct, Birgit? I think so. Yes, I think so. Okay, these are for I equal 1, this is the n plus 1, modulo somehow lower terms for the higher ones. Okay. Yeah. Okay, and then we compute what do we do next? Then to achieve this, we use the Birgit spectral sequence, right? So we so here we have a homology theory that has QNet formula, so we can apply the Birgit spectral sequence, which is given by this. So we need to compute the Hochschild homology of this algebra over this ground ring. And here, if we notice that this you can write as a colimit some Ci or Cl rings where C0 and then you just take somehow the L first parts of these, and then you notice that we have an isomorphism like this. Essentially, you think of this you have a adjointed some TL, and up to units you have a relation of the form like this. So the differential of TL is going to be trivial and will not contribute.
TL plus 1.
TL plus 1, thank you.
You mean p to the n, not p?
P to the n, yes. Thank you. To the n plus L plus 1. No, n. Yeah. So that's something that in the McClure, that McClure explained to me in a lot of details here a long time ago, but it somehow disappeared from the printed version of the paper. It somehow just says et al. But in the preprint on his homepage, you still have a very detailed, which actually is nice because it's actually what you have to prove that to show that it's et al. So then yeah. And finally, the spectral sequence. It's concentrated in filtration degree 0. So will collapse.
Are you sure what you said is right? I mean, when you go from the Hochschild for CL to the CL plus 1, you get something bigger. It's when you, I mean, because it's et al, you just get CL and CL plus 1, so it's just an inclusion. It's not an isomorphism.
You mean here?
Yeah. I mean, the Hochschild for CL is just a copy of CL, and the Hochschild for CL plus 1 is a copy of CL plus 1, so in degree 0.
Yep, something is wrong here.
Just the canonical inclusion from CL.
I mean, this is wrong also, right? I mean, no.
I mean, there's no higher Hochschild, that's the point.
Yeah, right,
CL
right.
It's just the algebra.
I mean, when you have a ring and you extend by this fashion, the Hochschild homology is going to be concentrated in degree 0. There are no differentials, right?
Yeah.
But I've already got confused here.
Well, you only want the Kn isomorphism.
Yeah, you want to key an isomorphism. But yeah, something is wrong here. Okay. Anyhow, the conclusion is that this is just that. So we have this isomorphism. Okay, that was the first piece where we hadn't to do too much computations. Right, so here somehow we had no assumption on En, because since the spectral sequence is concentrated on the degree 0, we don't really need the multiplicative structure on the spectral sequence to be able to compute it, which changes with the lower K series. Now if we take these numbers, then we find by similar methods, let's say, so we can compute the nth Morava K theory of En. So that's essentially supposed to be a Hochschild homology, the same as here, but here we'll need an assumption. So what is the answer? The new tensor with an exterior algebra over Fp, and then you have the differential on the classes on the right units, n plus 1. But this time the spectral sequence is spread in several columns, and we need a multiplicative structure to deduce its collapse. All the generators are in filtration 1, so as soon as we have a multiplicative structure, then we would have a collapsing spectral sequence. So this is assuming En is an E3 ring spectrum. Okay. And finally, it remains the rational part, which is easier. So rationally, we have an infinity structure by obstruction theory, and therefore we get a general formula. Like this, okay? Okay, so that's for the computation of the Morava K series somehow. So somehow the more involved part is that one, where I haven't said anything. And then we have somehow to assemble the pieces, and there's a and we do this for E2. So the next example in the chromatic picture of the Johnson-Wilson spectra. And we have a problem that the map that I mentioned earlier, this is not a module map in general. So you cannot use this map, for example, in the McClure-Staffeldt computation to detect the rational summand. You need to take a class, and then you take the module structure, and you take the summand generated by this class on the module structure. But to do this, we need somehow to lift the generators to homotopy classes. E2 module into E2 modules into THH of E2. We need homotopy classes. I mean classes in the homotopy group, right? So we have a lemma here that says that the first for E2, okay, just changing the generators. K1 of THH of E2, we can write it as Q1 E2 tensor the exterior algebra on DT1 and K0 the same, okay? And then, moreover, then you have classes in the homotopy groups. Lambda I in 2pi minus 1. And the product then that map to these classes, okay? Lambda 1 is going to map to DT1 and lambda 1, lambda 2 and lambda 1, lambda 2 will map to DT1, DT2 and DT1, DT2 rationally. And again, for doing this, to lift these classes, we'll use another HHH computation. Where was I? Yeah. So a proof, maybe a short proof. So the renaming of the classes, changing the classes is no problem because modulo units undecomposable, and in K1 we had well, same kind of formula, dv1 dv2 dv2, sorry. Is also congruent to that class. Okay, so that when you, this is a unit, and the differentials would be then correspond to a unit. Okay. So this allows you, just looking at the formulas for these classes, allows you to change the generators to get the one that come from BP, and so McClure-Staffeldt and then you need also a result of Bastera and Mandel to be able to compute HH of BP. But here it's really an integral computation. You have the integral homotopy groups. Okay. So McClure-Staffeldt do it under the hypothesis that you have an E-infinity structure, and then Bastera-Mandel proved that you have an E4 structure, so that the computation is actually valid. Right? And then now we have all these integral classes, and we just have to show that we can map them down and they will respect everything, so that we have constructed okay. Now we can glue the pieces together. Somehow we can state our the consequence of the computation we have done is that this inclusion of zero simplices into THH, we take the cofiber. In the case of E1, this is the piece that was computed as rational K-theory suspended, right? If E2 is an A3, so we we're going to need the module structure to be able to compute, to define the summand, if you want. We have splitting. Here the suspension are a bit random. They depend on the generators that we have chosen. We could have taken other. So you have L1 local piece, and then you have two rational pieces. Okay, and the degree just correspond to these classes lambda 1, lambda 2, and lambda 1, 2. But we cannot split, we do not manage to split the unit, inclusion of the zero simplices. So if I split, then for example, if E2 is commutative, so please someone, well, without that we have this, right? So, but if E splits, let's say for some other reason, then we would have HH of A2 then splits as 4 summands, right? So this would be the real generalization of McClure-Staffeldt's computation. I'll come back here. So the sketch. Here is that you, well, you map in your summand. So here we know by proposition 1 that this cofiber is L1 local. So we have maps. We have a map from this. Yeah, let's say. Like this. Okay, this is just the fact that we had this integral homotopy groups map. So this, let's call this G1, and then we can further map to the cofiber. And similarly, J2 and J1, 2 for lambda 2 and lambda 1, 2, right? So we claim that the sum of these maps, which is going to be these factors over the localization. Okay. Now that's more or less achieved somehow in a factor square, but we've noticed first that the first map, the map from the first summand into T bar is a K1 equivalence this time. Okay, so equivalence, and then you check that if you take the cofiber again, this time you get something irrational. Because this was a K1 equivalence. And then you are mapping the two pieces, the two rational pieces in here. And in fact, you can show that it is trivial when you go to the cofiber here. So that actually you can lift this map to T bar, but we don't know how to lift this to THH. We just can lift it to the cofiber if we don't have a splitting. Okay, so to generalize this to higher Johnson-Wilson spectra would be nice. We have two obstructions. Somehow here we have been able to rename the classes using the TIs. So DW2 was written in terms of T1, and then we know these are spherical. They come from the homotopy groups. That's a bit problematic for the higher Johnson-Wilson spectra, and then of course also the chromatic squares, factor square get also more involved. But from the computation, from the eyes of Morava K-theory computation, it seems plausible that something like this would be possible. So somehow in our preprint we conjecture that the story goes on. So how does it go on? In this case, the picture somehow is you look at the generators in the Morava K-theory computation, and here you have a piece of E2, L1 E2, and then L0 E2. And if you look at the computation for the rational homotopy of THHAN, you have classes DT1 to TTN, and we expect somehow that a similar splitting could happen. But there are a lot of questions here. Thank you.
If you assume E2 is commutative enough,
yeah,
What is the possible ring structure? I mean, is there? Do you have information about the actual ring structure?
Yeah, no.
Because
I mean, this is splitting as a module, right? And no, I mean the picture of K theory where we have this model as a KU algebra somehow is something we are missing here. I mean,
I was just wondering whether, you know, if you could understand that, whether you could stabilize
yeah, right, yeah.
what towards TH2.
Yeah. If we had, I mean, the formula for KU gives you the impression that KU is a Thom spectrum. It's the same formula that would hold for Thom spectrum. I mean, if KU was a Thom spectrum for a map from CP infinity into BF, you would have exactly this formula that I wrote down, which then account for this chromatic breaking into pieces by Ravenel-Wilson's computation. So if we had something similar here, I mean, if we had a conjecture that E2 was a rings, a Thom spectrum, for example, it would give you a multiplicative answer, but I don't know if there are such interpretations or even conjectures about it.
What would happen if you replaced the Johnson-Wilson spectrum by the Morava EF?
Yeah, I mean, that would of course have the advantage that you know you have a commutative structure, but on the other side, I don't really know how to compute THH of this kind of continuous. I mean, my impression is that we need a kind of continuous version of THH to be able to handle these cases. I wouldn't know how to integrally compute THH of Lubin-Tate spectrum, but that's why we fall back on somehow the Johnson-Wilson in this computation.
Any questions? All right, let's thank the speaker again.